wood and clay, wood and clay. Build it up with wood and clay, my fair lady. Wood and clay will wash away, wash away, wash away. Oh, wood and clay will wash away, my fair lady.
Presentation outline, we're going to talk about American Bridge just briefly, the company I work for and the company that has the prime contract to do the bridge removals and the new bridge construction. Talk about the project just a little bit, kind of what it entails as far as what's going to be replaced and what it'll look like when it's done. And then talk about the Fairfax Bridge demolition and spend most of the time talking about that. And then at the end, talk about kind of where we're at in the project today and what you should expect to see through the rest of the project. American Bridge Company was founded in 1900, headquartered in Pittsburgh, Pennsylvania. We do have an office in Overland Park. Around 1,000 employees, around $500 million annually in revenue. We have completed projects in 50 states and over 60 countries. The kind of the typical American bridge job is one that's complex or technical, design build projects, which the US 69 project is, or anything over water. For more propaganda on American Bridge, feel free to visit the website and check out some other pictures of past projects that we've completed. Talk about project overview. The project is replacement of the Fairfax bridges, along with some roadway work on the Kansas side and the Missouri side as well. On the Kansas side, it's pretty minor work. We connect the new bridge to the old roadway. Kindleberger, the intersection of US 69 and Kindleberger, will get new traffic lights, new pedestrian lights, new ADA compliant, new controlled intersection there. There will also be a ped path from Kindleberger all the way across the bridge and then all the way up to the Argosy Casino Parkway as well. The Missouri side of the project, a little bit different since there's a lot going on at that end. But if you're familiar with that area, Argosy Parkway from Horizons Parkway, you kind of take a lot of turns and go underneath the old bridge and come back again. Well, when the project is done, there'll be pretty much a direct shot in between the two locations, so that bad turn down there will be taken out of service. The bridge itself, it will be 2 lanes, 1 bridge, which will replace the 2 existing bridges. So it'll be 2 lanes northbound, 2 lanes southbound, and then a 10-foot wide bicycle ped path as well. As far as the project itself goes, it's a design build project, which means American Bridge, the contractor, is responsible for the design, obtaining all permits, regulatory approvals, utility relocation, coordination, and quality control. MoDOT and KDOT are participating in the funding. The work on the Kansas side of the river, KDOT's paying for, the Missouri side, MoDOT's paying for, and the bridge is being split between the 2 states. And MoDOT is being the lead coordinator on the project. In January of last year, January 2014, MoDOT had some industry meetings to kind of introduce the project to contractors and designers. In February, 8 interested bidders turned in statement of qualifications, and from there MoDOT shortlisted to 5. So there's 5 people that got to bid on the project. And from mid-February to the 1st of June, we spent time with MoDOT in weekly meetings kind of talking about what we think we want to do, get their feedback, ask questions, get clarifications on the project. In the proposal, MoDOT asked for, we want a bridge from here to here, and we want Argosy Parkway straightened out. From there, it was up to the design builder to choose what to do with that. A positive statement on MoDOT, the bid process and the project execution to date. They've been very open very easy to work with, answer questions in a timely manner, and a lot of DOTs aren't that way. MoDOT, the project team on this project is, we're really getting our bang for our buck as taxpayers with those guys. They're doing a fantastic job. So we worked from February through June with MoDOT on the bid, turned in the bid the 1st of June. From 1st of June till the mid-July, MoDOT evaluated the proposals, and a design build project doesn't necessarily mean that the low bidder gets the work. It's the best value. There were 4 areas that MoDOT scored on, 500 points for price, 200 points for traffic control or impact on traffic, 200 points on bridge durability. They wanted a river span bridge that was very durable, low maintenance. It's going to last forever, and it's not going to cost much to keep it up. That was worth 200 points in the evaluation. And then 100 points on the contractor's safety program. So in theory, you could be the second or even third bidder in price, but if you have the best value based on the other items, you score the highest. But with 500 out of the 1,000 points being in price, you pretty much had to be the low bidder to get the work. We were notified in July that we were awarded the project. By the end of August, we had the whole project team co-located in a project office in Riverside. The project teams consisted of MoDOT personnel, American Bridge personnel, Garver, who was our engineer, several of Garver's sub-consultants, and some engineers from Burns & Mack, who were the owner's engineer. We have upwards of 27, 28 people in the office. They're all, the various groups that are involved in the project are all in the same office. I sit right beside Lisa, who is a project director for MoDOT, who sits right beside our quality control guy. Across the hall is the lead roadway design engineer, who sits right next to the Burns & Mack owner's engineer. Everybody's intertwined in the project. So we started in earnest, co-located in August. In September, we actually started construction. So we were basically there a month, and we started construction, which is another positive of the design build aspect. We started with a crossover to get traffic off a southbound bridge, the Fairfax Bridge, so we could demo it. And then we started the demo work of the Fairfax Bridge. And of course, that's what we'll spend most of our time talking about. The Fairfax Bridge is a truss bridge. Kind of the general removal scheme is to take the deck off the bridge first, get that out of the way, and then selectively cut pieces of the bridge up so it can aid in the shooting of the bridge or the explosive demolition of the bridge. After you make the shot, then you basically clean up the mess then, and process that material. The demolition of the bridge required a lot of engineering, construction engineering. On this project, the demolition is by far the most engineered construction part of the job, and did take more planning than any other element of the bridge itself, any of the new construction. What we were doing to the bridge, it was not supposed to happen to it. You're not supposed to tear a bridge up. So there was a lot of engineering, a lot of planning that went into that, and a lot of safety considerations as well. Anytime you tear something apart, it leads itself to unsafe conditions. So there was a lot of effort put into that as well. And of course, with any great plan, there's going to be changes. Something's not going to be like you expected it to be. The as-built plans didn't match. The flow of the work didn't work quite like you thought it was going to, and you have a bottleneck somewhere, so you need to tweak your plan a little bit. For the Fairfax Bridge demo, the biggest change that we came across, originally we were only supposed to have 2 demolition shots to shoot the whole bridge, and we ended up with 4. We started the demolition process and the river iced up, so we couldn't get into the river. So we went ahead and made a couple shots on the spans that were over the land that we could get to. And then when the river cleared up, we got back in the water. So we kind of had to change our plan based on the weather conditions as well. This picture says a lot about the demolition. The very first thing we did is the Fairfax Bridge is a little different than the Platte Purchase Bridge, which is a northbound bridge. But the Fairfax Bridge, the bridge deck is metal grading that's infilled with concrete and then has an asphalt overlay on it. So the first thing we did was go out there and mill all the asphalt off. And then you come through and punch holes in the concrete deck where the metal grid is at, so we could actually get to it to torch it loose. So go ahead and remove the deck. The square holes in the deck are the rigging holes, so we could actually rig to it and grab that deck segment and remove it. And what's laying there off to the side is actually one of the deck segments that was removed. The bridge itself, the portion of the bridge that was over the river and over the levee, we went ahead and removed all of the deck and the stringers. We needed that truss to be as light as possible, so when we shoot it and it falls down, when it lands on the levee, it's a reduced impact to the levee. And over the river, to reduce the weight of the truss, because we have to go back into the river and pull those pieces out. But the pieces that were over the land, the weight wasn't that big of a concern. However, during the demolition process, various stages of the demolition process, if we left the concrete in the metal grid deck, we would have overstressed some of the members and caused some problems. So we went ahead and removed the concrete. So this portion of the bridge is from the Missouri side on the levee looking to the south, and we removed all the concrete in that deck. And went through there with a little excavator with a hammer and just beat the concrete out of the deck. And here's a picture of the actual grid deck removal. We have an excavator that's rigged to the piece, and have the guy out there with a lance that's torching the metal grid deck to remove it. And once that grid deck is cut, we'll go ahead and pick the piece of the deck off and swing it behind us, and then go on to the next one. Each one of those segments weighed in between 6,000 and 7,000 pounds. And here's a picture of the deck being removed when we're over the river. And as you can tell, everybody that's been on that old bridge, it's not very wide, and it even gets narrower when you put construction equipment up there. It's a pretty tight fit. But the grid deck was removed, and then the stringers were removed. It's a little hard to see, but there's the stringers that were removed. So we'll remove 3 or 4 pieces of grid deck and then remove the stringers. That's another effort to reduce the weight. And there's the stringers that are off to the side of the bridge after they've been removed. So now we've got the grid deck off, or we've beaten the concrete out of the metal decking. Now it's time to do the prep work to shoot the truss. Through the engineering of the demolition, which was done by a local firm, Genesis Structures, it was determined, that it pains me to say this, but we had to strengthen the truss before we shot it. And there were several locations that during the different phases of removal, the truss was overstressed, so we had to strengthen the truss in a few places before we tore it apart. So we did that, and then the pre-burn, and that's where you go in and selectively remove portions of the truss before you load it and shoot it. And we'll see some pictures of what pre-burn is. Then you load the shot, shoot the truss, and get all kinds of people with cameras out to look at that, and then fish the truss out of the river and then process the truss. This is a picture of the pre-burn. This is actually from a different bridge, but it's a very good picture. Very similar to what we did on the Fairfax Bridge. The linear shape charges, which will go in that slot that we've cut out there, they're very predictable, they're very efficient, they're very reliable. However, they are not as reliable when they have to go through 2 and 3 pieces of 2 or 3 layers of metal, or have to make a turn. That's not what it's for. It's a linear shape charge. It shoots in a line. So cutting off these pieces helps with the shooting of the truss itself. And that's another engineering thing. You take a portion of the section of the member out. Is the truss going to stand up? So that's another engineering check that had to be done. And here's doing the pre-burn on the Fairfax Bridge itself. We have guys in man baskets, guys in manless. They go through and make those cuts all the way through on the bridge. We just do the pre-burn on the portion of the bridge we're going to shoot. You don't do the pre-burn for the whole bridge and leave it exposed. Through the engineering, we looked at this bridge with a 90-mile-per-hour wind. So when you do the pre-burn and reduce the capacity of the truss, through short-term loading and a bunch of factors, it basically gets down to 67 miles per hour. So that bridge would be fine in a 67-mile-per-hour wind, even though we've taken away some of its capacity. That's another part of the engineering. And that's the important part. Those are the linear shape charges. It's basically C4 clad in copper. They're basically a long cigar. They don't look too intimidating, but they do their job very well. They're highly controlled as well, so you probably won't see any of these laying around anywhere. But those are the shape charges. And the yellow cord at the end is the detonation cord that gets wired to the rest of the bridge to make it go. Here's a shot of when the truss is actually loaded. You can see the pre-burn work that was done to cut out a chunk of the bridge, and then the shape charge installed. I'd be remiss if I didn't point out the high-tech rubber band from Staples and the chunks of styrofoam that are used in this process as well. But that's a loaded location where the shot's going to go off. The detonation cord is wired to that already, and we also have, which is pretty important, some shot covers that are made out of wood. The next step in this process after it's loaded and wired up is the shot cover slides down and protects that. And we'll talk about the shot covers a little bit later, but that's a location that's ready to go. Here's another picture of a location that's loaded. One thing to look at, I want to point out, is the linear shape charge. It's a V-shaped. It actually has a direction, so you need to make sure you have it pointed the right direction when it's loaded and ready to go. Here's a picture of the Fairfax Bridge. It's pretty close to being ready to shoot at this stage. We have the linear shape charges in, the detonation cords, which you basically see a string that's falling everywhere, are in. We have our shot covers over the locations where the shape charges are at. And we also have a used piece of conveyor belting that went over the shot cover on the bottom cord on the bridge that faced the Platte Bridge. The Platte Bridge has several utilities hanging from it. So we wanted to make sure, the belt and suspenders kind of thing, make sure nothing got over into those utilities. The shot covers are fine, but we went ahead and put the conveyor belting on it as well just to make sure we didn't have any problems. Now we get to the fun point of shooting the truss. It's all loaded, it's ready to go, and we get to shoot the truss. Garver, our design engineer, had a drone, so they ran it over when the shot was being made, the first shot of the span that's over the river. It's really a good video. There's probably several on YouTube as well. This picture is actually from another project that we shot. First of all, I really like the picture, so I tried to get it in wherever I can. One thing I wanted to talk about, and it may be a little hard to see, but there are the wood shot covers we talked about before. There's pieces of those flying right now in this shot. You can see the splashes in the water. They only got about 25, 30 yards away from the bridge, but they did their job. There's really three things that can go wrong with a demolition shot. You have projectiles, and what gets blown up is not a portion of the bridge, it's that copper cladding that's on the shape charge. The bridge doesn't get blown up. The shape charge actually cuts the bridge like butter. It's really pretty intimidating, to be honest, but it cuts it like butter. So the projectile is not a part of the bridge. It's actually that copper cladding of the shape charge. And that's what you have to knock down or slow down with the wooden shot covers or the conveyor belting. The other thing, shooting a bridge is not like shooting rock. When you shoot rock, you have ground acceleration. When you shoot a bridge, you are not going to crack somebody's swimming pool or crack their foundation. There's just no ground acceleration. However, there is air blast, air pressure. That actually probably causes more damage than anything else, especially if it's a cloudy, overcast day. The air pressure will blow out windows if you have windows that are close to where you're shooting at. So it's something to be aware of. We were fortunate on a few of these projects that we were far enough away from houses not to worry about that, but actually the air blast pressure causes more damage than projectiles if you cover the shape charges correctly. And that's what happens. There's a piece of copper right there. It was the cladding on the shape charge, and of course copper is really soft. It was driven like a nail through those two sheets of 3/4 inch plywood. So if you don't have your covers on, that piece of copper is going to go flying. But with the covers on it knocks it down, so it's really not an issue. This is a picture after the first shot we did, which we actually shot. There's two 300-foot truss spans kind of on the overbank on the Kansas and the Missouri side. We shot those first. This is a picture after we made the shot. It's laying on the ground. We also protected the levees on both sides of the river with crane mats just to lessen the impact on the levee as well. That's another picture of the same shot, just from a different angle. That's a picture of the truss on the Missouri side after our last shot. The last piece fell down. The only thing that didn't come down, which is the king post, which that's the piece that sits on the pier. And on every video, it's always the last piece that falls over. And it fell over where we wanted it to, but then we had to figure out how to get that down off the truss that was there. It came down fine, but it's kind of intimidating to walk up and see that, though. This is the fun part that nobody sees. This was actually removing the truss from the river. Since the Missouri is a navigable waterway, we had 24 hours to remove the truss that we shot that landed in the river in that navigation span, and then another 24 hours to remove the truss pieces that were in the water but not in the navigation span. So this is what happened after the shot when all the cameras left. What we do there is, of course, the pieces are in the river. We rig to the pieces, lift them out with a crane, set them on a barge. The barge brings them to the shore. Have another crane on the shore that picks up the truss piece and puts it on the bank where it's processed. Sounds pretty easy. And here's the truss, one of the truss pieces coming out of the water. And From my point of view, honestly, I'm more worried about this kind of work than I am when we actually make the detonation. Like I said before, the linear shape charges, they're very efficient, they're very reliable. You know what's going to happen as long as you take a few precautions. This kind of work, we're fishing 80 to 120,000 pound pieces out of the river that have just fallen 100 feet, hit the water, and probably hit another piece of the truss at the same time. And the work is at night. This work worries me more than the actual shot does. This has got more potential for things to go wrong and the people to get hurt. Not to minimize the actual shooting of the bridge, but this is something that it has to be planned and thought through, and have some good people doing the work. But here we are removing the piece of the truss from the river. There's another piece that's removed from the river. The pieces were cut in such a way as so that we had enough crane to pick them up. This piece is only about 30 lineal feet of the bridge, but it weighs 80 to 90,000 pounds. The previous piece is about 60 lineal feet of the bridge, and it weighs about 100,000 pounds. So the location where we actually shot the bridge was dependent upon the crane size, how big of a piece we could get out, and also the engineering part of it. So you're doing a dance with that all the way through on the planning. And there's another piece that is on the barge itself. Those are the kind of things that make you worry, because that piece of truss has been deformed due to the shooting and getting it out of the river. You just have to be careful that you rig it right, and you also land it on the barge in a manner that is very stable, because that still has to make a trip across the river. And there's that piece being lifted off the barge and put on the bank. And the excavator in the foreground is, once that piece lands, it will go ahead and process that material. The excavators have mechanical shears, which are huge scissors that will swallow those members and cut them in half. There's another piece that's coming to the bank right now. At the same time, it's kind of in the background, the crane on the water is actually rigged to another piece and lifting it out of the river. So shortly, this barge will take off and get back here and accept another piece. So it's everybody's in motion when it works right. Well, this video is one of the guys that was actually doing the processing work, set it up on the dash of his truck, and it's time lapse. It goes really fast, but it shows the process of the work at night. A few of the pieces that came out of the river were too heavy for the crane on the ground to handle, so we had to cut those pieces in half and get them off the barge and get them on land. I think this was actually a video of the first night after the 24-hour, and we had a really good night there. I think we got 7 or 8 pieces in a 12-hour time frame, so it worked really well that night. And of course, the truss, when it's demoed and removed, you're not done. You have to take the piers out as well. This is a picture of the center pier, the one in the middle of the river. It was taken down with a mechanical hammer down to the water level, and they're finishing up that removal right now in this picture. This is the only pier that's in the water. The rest of them are on the ground, which makes it a lot easier to remove them. Here's a picture of the pier removal on the ground. That excavator is a long reach, and it can reach 95 to 100 feet up in the air and beat those piers down. But the pier out in the center of the river, we had to take down to where the river's at today, about 30 feet below the water elevation, which entailed shooting it as well. So at this elevation, we've already drilled the holes in the top of the pier and loaded it, and we're putting crane mats on the top of the pier just to contain the fly rubble. And we'll actually take the detonation cord from this pier and take it up to the Platte Bridge. And then we go down the bridge about 100 feet and cower behind the barrier wall and push the button. And that demolition, that went well. All the rubble that's in the river from this removal we have to take out, of course, and we're just about done with that right now. These next couple pictures are showing the demolition of the approach spans. All the attention was put to the main spans over the river, but there's also several approach spans that are kind of intricate in their removal as well. They're 80-foot simple truss spans. There's not a whole lot of bridge there, but we will go ahead and have the same process, remove the deck, and then remove the truss. The difference on the approach spans are that we can remove the deck with bigger cranes because we can get to it. This picture is showing part of the deck being removed. This is on the Missouri side. I guess this may be a little bit of an odd place for this slide, but wanted to point out that everything on the demolition work, all the material was recycled. The asphalt that got milled off the riding surface is being reused in asphalt pavement. The structural steel, the rebar, were both scrap. They're going back to be reused. The concrete rubble from the metal grid deck and from the piers will be processed and used on the project as either as fill or a ditch liner or something like that. So everything that came out of the old bridge is being used somewhere. Another interesting part on the south side of the bridge, there's the UP Railroad has a yard in there, and of course we have to remove that bridge that's in their yard. So we got a few days to get in here, and of course you have to build the road in the morning when we get track and time, then get the crane in, get the deck sections off, which we loaded onto a lowboy and then hauled out of the rail yard. And then get the crane back out again and pick the road up again, all in the day, so they could get the rail yard back open to use to shuttle cars around. And there's a picture of picking the truss. Those are 80-foot spans, and they were light enough that we could grab the whole span at once, which was really beneficial considering the time constraints of working in the UP rail yard. That's kind of the really quick discussion on the demolition part of the project. Kind of want to talk about, just for a few minutes, about the new construction, the things we're doing now to build the new bridge. The new bridge is kind of a typical bridge in some respects, a drilled shaft foundations and plate girder bridge with full depth of deck. So it's really not anything too extravagant. Some of it's kind of big, but it's nothing too exotic. This is a picture of starting the drilled shaft construction, and what's on the hook right now is the template for the drilled shaft. And the drilled shaft consists of a 10.5-foot diameter steel casing that's 100 to 110 foot long, that's put in through the muck, through the overburden, all the way to rock. And then we'll drill about another 20 to 25 feet into rock to make the drilled shaft foundation. But this is the template to aid in getting that casing in the right spot. This is another picture of the template along with the casing that's partially installed. And that's part of the installation process of the casing. Like I said, in this particular situation, the casing need to be 100 foot long. Of course, that's too big, too heavy to handle. So we have two pieces of the casing. Go ahead and drive the first piece. What's on top of the casing is a vibratory hammer, and that drives the casing down. We set the first casing down, grab the second piece, weld it to the first piece, and then continue driving until we get to bedrock. Once it's down to bedrock, a drill attachment cleans out everything inside the steel casing, cleans out all the muck, the sands, the gravel, and then eventually cuts the rock socket in. That's the 20 to 25 foot of rock below the casing. Once we have this 100 to 120 foot long hole in the earth, we set a rebar cage in the hole. This cage is approximately 135 feet long. It's for a drilled shaft that's on the levee on the Kansas side. The vertical bars are laid out, for a better word, in a pile, and they're rigged to this framing and lifted up. At that point, it's basically a huge wind chime. All the vertical dowels are hanging there, and then we lower the cage into the hole and put the horizontal rebar in the hoops at that stage. Get the rebar clear down into the drilled shaft casing and fill the hole up with concrete, and we have a drilled shaft foundation. These drilled shafts are 250 to 350 yards per drilled shaft of concrete. There isn't just a river crossing bridge in this project. There is some other roadway work. This is another bridge. There's two bridges on this job. Of course, the river bridge is 2,200 feet long and 78 feet wide. This bridge is about 38 feet long and 20 feet wide. It's where the new northbound 69 will tie into 635. And it's going over the new Argosy Parkway. It will, I talked about earlier, taking that big kink out of the road. The new Argosy Parkway will go underneath this bridge. This is also on the Missouri side of the job. This path right here is a temporary ramp. That's been open since October. That's what gets traffic from southbound on head-to-head traffic on the Platte Bridge. This temporary ramp, which we will hopefully open Thursday, will get traffic off of the old northbound 69 and onto this new ramp and over that big bridge I just showed you, the little 38 by 20 foot bridge. And once the traffic is off the old northbound 69, that will allow us to build a roundabout here at Argosy Parkway and complete really get a big chunk of the roadway work done on the north end of the project. If you're interested in the status of the project, MoDOT puts out a monthly newsletter. You have to sign up for it and they send it to you via email. There's also a website. You need to go to MoDOT on the major projects tab and look for the US 69, and they have updates of where things are at, pending traffic changes and items like that. So if you want to kind of keep in touch with what's going on with the project, you need to visit the website there. As far as the rest of the schedule of the project, we're hoping to have the roundabout open that we talked about at Argosy Parkway mid-June. And then the traffic pattern pretty much stays the same until we get the bridge completely done, which is by December of 2016. And then we have till July of 2017 to remove the Platte Bridge. So we'll be doing more demo work in the winter and spring of 2017 as well. Any questions?
Build it up with wood and clay, wood and clay. Build it up with wood and clay, my fair lady. Wood and clay will wash away, wash away, wash away. Oh, wood and clay will wash away, my fair